Hi. So now that we have learned a lot about ionic compounds, we're going to actually jump ahead to chapter 9 because the way that our textbook structures it is we learn all about ionic compounds, then we learn all about covalent compounds, then we learn how to name them. And so I like to just do the naming part as we're learning about them. So that's what this lesson is going to be on. And we're also going to introduce the concept of polyatomic ions, something very important in chemistry. So of course, the screen in front of you should be very familiar now. This is the table, the periodic table, but colored in to show the patterns of ion formation. So that the first column, those alkali metals always form 1+ ions. The alkaline earth metals form 2+ ions. The transition metals and the P block metals can have a few different ionic charges, but aluminum is always 3+. Then we sort of skip the next column because it is very diverse with nonmetals, metalloids, and metals in it. The nitrogen's column always gains 3 electrons to form 3- ions. Oxygen's column gains 2 to form 2-. The halogens gain 1 to form 1-. And of course, the noble gases are grayed out there because they do not form ions. So how do we name them? The naming of the cations, the positive ions, is very easy. All we need to do is say the name of the element plus the word ion. So literally, if I say Na, that's sodium, and specifically the sodium atom, because it has all of its electrons. And if I say Na+, that would be the sodium ion. Literally, you just add the word ion after it. Now, this gets a little bit tricky when we get to the transition metals. The reason why I don't need to say the charge on the sodium ion is because sodium always forms a 1+ ion. So if I just say, the aluminum ion, you know that the aluminum ion must be Al3+, because aluminum doesn't form any other ions other than 3+, right? The calcium ion, that must be Ca2+, because calcium doesn't form any other ions besides the 2+ ion. But what if I said the iron ion? Well, you might be wondering, which one do you mean? The iron 2+ or the iron 3+? And so that's where we need to do one special thing. If it is a transition metal that could have more than one possible ionic charge, we just need to use a Roman numeral to say the charge of that ion. So if I am meaning the iron 3+ ion, I would have to say iron, and then in parentheses, the Roman numeral for 3, and then the word ion. And if I mean the iron 2+ ion, I just say iron, parentheses, Roman numeral 2, ion. The chart, table 9.2, just goes through some of the more common transition metals and the possible ions that they can make. And the reason why I am just pointing this chart out is because I want to show you that this is a sort of the newer naming system. I don't know. It was new when I was in high school, so it's new-ish. But to actually use the Roman numerals, that's actually the newer version of this. The older version was to use suffixes called ik and us. And so if you meant the lower charged ion, that would end in us, and the higher charged ion would end in ik. So there would be ferrous and ferric. So we also went back to their Latin names. For many of the transition metals, their symbols don't match their name because they're in other languages. It was very confusing. So we do not really use this anymore. But if you have an old professor in college, or you might be reading a textbook, they might be using those terminologies. So I just want you to know they exist. We will only be using these. And you don't have to have any of them memorized, because I will always tell you what is the charge of the ion, or you'll be able to figure it out from the problem. And so those are how we do cations. Now we need to do, how do we name anions? So how we name anions is we just change the ending of the word to IDE. And you've probably already heard me do this a bunch of times. So when I say, Cl-, or when I'm referring to that particle, that is called the ion, right? And you know this already because you know we call it sodium chloride, right? So anytime O2 minus, that's oxide. F minus, that's fluoride, right? Phosphide, nitride, bromide, iodide. Those are really the sulfide. I'm like, those are really the only ones that we will use. So now all we do to name the actual compound is name the first element, then name the second element. That's it. So KBr, K is potassium, so I just write potassium. I don't need to use the word ion because it's in a compound. And then bromide. Right? Na2O is sodium oxide. And this is a mistake that a lot of students make is they want to somehow incorporate the 2 in there, like sodium 2 oxide or sodium dioxide or disodium oxide, because there's only one way for sodium, which has a +1 charge, and oxygen, which has a 2- charge. There's only one way for those to come together to make a neutral compound. I don't need to say anything other than sodium oxide, because if I say sodium oxide, everyone is going to know that that must be the formula. And then if I move on to FeCl3, I need to remember, and this is where it gets tricky, I need to know the transition metals so that I can recognize them, because when I see a transition metal, I need to realize I'm going to need to use a Roman numeral. So this would be iron, and then a Roman numeral depicting the charge. Now I'm going to have to almost reverse engineer, reverse crisscross this to figure out, well, what was the charge on the iron? And if I know that for every 1 iron, it took 3 chlorines, and chlorines are negatively charged, -1 charge, that must mean this iron must have been 3+. And, most of the time you can reverse crisscross that in order to figure that out. So this compound would be iron 3 chloride. CuO is a little trickier. So I know it's going to be copper, it's going to be some sort of Roman numeral, and then oxide. Again, what was the charge on the copper? I need to think about it. In this case, I'm not going to be able to reverse crisscross, because is this copper 1? Well, no, because think about what's really going on here. I have 1 copper for every 1 oxide, and if oxide is 2-, this copper must have been 2+. You have to think about it logically. So I can't always say, hey, just reverse crisscross, that'll always work. It will work most of the time, but not all of the time. You really need to think about what is actually going on, what is actually making this compound neutral. Okay? So then we get to polyatomic ions. This is probably a brand new word for you. Think of what that word actually means. Poly means more than one, atomic, atom, ion. So an ion made of more than 1 atom, and that's basically it. The atoms they themselves are covalently bonded to each other. But since in the group there's an unequal number of protons and electrons, it overall has a charge. So here are some examples. The ammonium ion. Ammonium ion is 1 nitrogen surrounded by 4 hydrogen, and those little lines, that stands for the covalent bond. But overall, if I were to count the number of protons and electrons, this would have 1 more proton than an electron, and therefore it overall has a +1 charge. Nitrate, right, is this blue, is the nitrogen in the middle, 3 oxygens on the outside. It has 1 more electron than a proton, so it has a negative charge. And here is a table of all of the most common polyatomic ions. There's many of them, and this is only a small subset of the most common. And the ones that are bolded are the ones that I'm going to make you learn for the test, memorize. So this is get out your index cards, make flashcards, you're checking, if you have 5 minutes at the end of class, you're flipping through your index cards to memorize these polyatomic ions. And the reason why we're asking you to memorize these is because they're in some ways more important than many elements. Tellurium, we're never going to use that element, but nitrate, it's in the food that you eat almost every day. It's all around us. Phosphate, that's part of DNA. Right? So these are so super duper important. So if I were to, let's go through these, the ones that are most important. The first one is acetate. Acetate is related to acetic acid, if you've ever heard that. CH3COO with a negative charge. Now, you can also think of that as C2H3O2, but we write it out the way that I did earlier because that is going to give us some information about how the bonding is. It doesn't seem all that important right now. It will in a few chapters. The other -1 ions that I'm going to ask you to memorize are hydroxide. All of the strong bases are compounds that contain hydroxide. Nitrates and nitrites, these are in a lot of foods. So those are all the -1 ions. Then we get to the -2 ions, carbonate and sulfate and sulfite. And you may notice that there's a little pattern going on. Like we did nitrate, nitrite, we did sulfate, sulfite. There's a lot of other polyatomic ions that follow that same pattern. At the ending of the polyatomic ion, you'll often see either the word ate or ite. That's a clue that you're talking about the polyatomic ion. And the ate will always be the one with the more oxygen. So almost always, if it ends in ate or ite, it means that element plus oxygen. So phosphate, that's the next one that we could look at. Phosphate, phosphorus, and oxygen. Sulfate, sulfur, and oxygen. Carbonate, carbon, and oxygen. Nitrate, nitrogen, and oxygen. Okay? And the ate is always the one with the more oxygen. So again, there's one 3- ion that I'm going to ask you to learn, phosphate, and the only positive polyatomic ion. So all the other polyatomic ions could be put on a test, but I would have to tell you, perchlorate and then give you the formula for perchlorate. But if I say nitrate, you're gonna need to know what nitrate is.